I want you to imagine an element, like just a single box on the periodic table.
Right, element 28.
Yeah, exactly, element 28. And it's currently playing out what has to be, the most intense contradiction in the history of our planet.
It really is a staggering duality when you look at the source material.
It's wild because on one hand, this element literally generates the invisible magnetic shield that, protects everything on Earth from deadly space radiation.
Right.
And right now, today, it's pretty much the absolute beating heart of the whole clean energy revolution.
But it has a very dark side.
It does. It has this incredibly dark, almost, I don't know, villainous history.
Yeah.
We're talking about a metal that served as the primary biological trigger for the single worst mass extinction Earth has ever seen.
Yeah, you're looking at a foundational building block of the universe that, well, it acts as a planetary savior in one context and then a planetary executioner in another.
Which is just crazy to think about.
It is. And it all depends entirely on where it sits in the Earth's crust, what it's bonding with, and what kind of microscopic life forms happen to stumble across it.
And that is exactly what we are getting into today. Welcome to our deep dive into the source material on nickel.
It's going to be a fun one.
It is, but I want to be clear right up front to you listening. This is not like some dry chemistry lecture.
No, definitely not.
The material we've pulled together covers this wild, spanning narrative. We're going to explore the exploding hearts of dying stars and slowly cooling meteorites.
Not to mention toxic plants that literally bleed green sap.
Right. And the extreme mind-bending physics happening inside modern jet engines.
And of course, how the extraction of this metal is currently reshaping global geopolitics, which is forcing us into some, well, very uncomfortable environmental trade-offs.
Yeah, the trade-offs are intense. So let's just start at the absolute beginning. Before it's in a battery, before it's even in the Earth's core, where does nickel actually come from?
Well, to find its origin, we have to look away from Earth entirely.
Right, out into space.
Exactly. We have to look at the terminal stages of stellar evolution. Yeah. We're basically talking about supernovae.
So dying stars.
Specifically, type Ia supernovae. Because to really grasp what nickel is, you have to picture a binary star system.
Okay, two stars orbiting each other.
Yeah. You have a white dwarf, which is this incredibly dense, dead remnant of a star, and it's locked in orbit with a companion star.
Right.
Over time, the white dwarf's gravity is pulling gas and matter off its companion. It's essentially gorging itself. But a white dwarf can only get so massive before the physics just kind of break down.
Right, there's a weight limit, basically.
Exactly. It's called the Chandrasekhar limit. And when it hits that critical mass, the internal thermal pressure can no longer withstand the crushing force of its own gravity.
So it collapses.
It collapses inward, yeah. Which spikes the temperature to billions of degrees.
Yeah.
And that triggers a runaway thermonuclear disruption. The entire star explodes. And inside that incomprehensible flash of heat and pressure, this microscopic assembly line kicks into overdrive. It's a sequence called the alpha process.
Okay, I've heard of alpha particles. They're basically just helium nuclei, right? 2 protons, 2 neutrons.
That's exactly right. During this catastrophic explosion, the star is frantically trying to fuse heavier and heavier elements together just to survive.
Okay.
So it takes an isotope called silicon-28, which is already present in the star. And in a fraction of a second, that silicon-28 captures an alpha particle to become sulfur-32.
Oh, I see. It's stepping up.
Yeah, then it captures another to become argon-36, then calcium-40, and so on. It's just rapidly stacking these helium building blocks.
Okay, I'm just doing the math in my head here. So, if it captures 7 of those alpha particles, 7 times 4 is 28. Add that to the original silicon-28, and you hit 56.
And there you have it, nickel-56.
Wow.
But here's where the universe throws up a roadblock. That alpha process stops dead at nickel-56.
Wait, why? Why does it stop there?
It represents a fundamental limit in stellar physics because of something called binding energy per nucleon.
Which means what, exactly? Like, in practical terms?
Well, think of it like rolling a boulder down into a valley. Every time the star fuses lighter elements together, the boulder rolls further down the hill, releasing energy that powers the star.
Okay, that makes sense.
Nickel-56, and eventually iron, are sitting at the absolute bottom of that valley. They are the most tightly bound, stable atomic configurations possible.
So they can't roll any further.
Right. If the star tries to fuse nickel into anything heavier, it's like trying to push that boulder back up the other side of the valley. It doesn't release energy anymore. It actually requires it.
So fusion goes from being an energy source to like an energy drain. The engine just stalls out.
It stalls out violently. The star blows itself apart completely.
Jeez.
But the fascinating thing about that nickel-56 forged in the blast is that it is highly radioactive. It has a half-life of only about 6 days.
6 days? That's really short.
Very short. Very quickly, it decays into cobalt-56. And then, over a half-life of about 77 days, that cobalt decays into stable iron-56.
Wait, hold on. If it decays that fast, then when astronomers are looking through telescopes at a supernova that exploded, millions of light years away, what are they actually seeing?
They are seeing the glow of radioactive nickel.
You're kidding.
Not at all. The physical explosion of a supernova is over in seconds. But that brilliant, intense light curve that we observe shining in the night sky for months or even years.
Like the SN 2012 supernova that the Hubble Space Telescope photographed.
Yes, exactly like that one. That light is powered entirely by the radioactive decay of nickel-56, turning into cobalt and then iron.
That is wild.
The photons hitting the telescope lens are literally the death rattle of those massive atomic collisions.
The light of a dying star is essentially just a giant cosmic nickel-powered nightlight. That is unbelievable.
It really puts it in perspective.
It does. So this explosion blasts all this newly forged nickel and iron across the universe as stardust, and over billions of years, it clumps together.
Right, gravity takes over.
And that's how we get our solar system.
Yeah.
Which brings us to the actual formation of the rocks flying around our sun.
Yeah, so when the swirling cloud of gas and dust that became our solar system started to cool and condense, the nickel strongly partitioned with the iron.
They stuck together?
They did. They stuck together in metallic phases. As the very first early asteroids formed, they grew hot enough from radioactive decay and collisions to actually melt.
Okay.
And the heavy liquid iron and nickel sank to the centers of these bodies, forming solid metallic cores surrounded by a rocky mantle.
Just like Earth.
On a much smaller scale, yes. But the early solar system was, well, it was a violent billiard table. Catastrophic collisions shattered many of these early asteroids.
Just smashing them to pieces.
Exactly. Cracking them open like eggs and flinging fragments of their deep metallic cores out into the freezing vacuum of space.
And when those fragments eventually cross paths with Earth and, survive the atmosphere, we call them iron meteorites.
We do.
And these specific meteorites hold a massive clue about nickel, right? I read in the source material that there's a pattern hidden inside them that you literally cannot find anywhere else in nature.
Yes, the Widman-Stettin pattern. It is arguably the most beautiful and diagnostic texture in all of geology.
What does it look like?
Well, if you take one of these iron meteorites, specifically a type called an octahedrite, and you cut a slice of it, polish it mirror smooth, and then just lightly etch it with a mild acid.
Okay.
This striking geometric cross-hatched crystalline structure is revealed.
I think I've seen pictures of this. It looks like, modern art or alien geometry.
It really does.
It's just these overlapping silver blade-like crystals locked together at perfect angles. But why do you need acid to see it?
Because the pattern is made of two different iron-nickel alloys that react differently to the acid.
Oh, I see.
You have camosite, which is relatively low in nickel, around 4 to 7%, and you have taenite, which is high in nickel, often well over 20%.
So the acid eats one faster than the other.
Precisely. The acid eats away the low nickel camosite faster than the high nickel taenite, which makes the taenite blades stand out in beautiful 3D relief.
But why is this an alien fingerprint? Like, with all our modern furnaces and metallurgical labs, why can't we just melt some iron and nickel, mix it up, and recreate that exact pattern here on Earth?
We can't recreate it because we simply don't have enough time.
Time.
Yes. When the core of that parent asteroid first solidified billions of years ago, the metal was a single, uniform phase of taenite. But remember, this asteroid core is floating in the deep freeze of space, insulated by miles of rock.
Right.
It cooled at a rate that is almost incomprehensible. We are talking about dropping just 1 to 100 degrees Celsius every million years.
Wait, 1 degree every million years?
Every million years. At that impossibly slow rate, the solid taenite becomes thermodynamically unstable. The atoms actually start to migrate through the solid metal.
Through solid metal. That's hard to wrap my head around.
It is, but over those timescales, microscopic plates of camosite slowly precipitate and begin to grow along the octahedral planes of the crystal lattice.
Oh.
It takes millions upon millions of years of solid-state diffusion for those crystals to grow large enough for a human eye to see them. It is a physical structure forged by deep time. You really can't fake it in a lab.
So when you hold one of those meteorites, you're literally holding the frozen history of the solar system. That is so cool.
It really is.
But it's also a perfect mirror for what's happening right beneath our feet, isn't it? Because Earth went through that exact same density sorting process.
Yes, the iron catastrophe. During its infancy, the early Earth was subjected to so many massive impacts that the entire planet was pretty much a completely molten ball of magma.
Just a giant lava ocean.
Exactly. And this allowed the dense metallic liquids, again, the iron and the nickel, to sink all the way down to the center of gravity.
So they formed our core.
They formed our planet's core, leaving the lighter, rocky silicate mantle floating on top to eventually form the crusts we live on. Today, the Earth's core is an immense iron-nickel alloy containing roughly 5 to 20% nickel.
And here's where we hit a massive turning point in the story of this element in our deep dive.
How so?
Well, because if that core were just a ball of pure iron, without that nickel impurity, we wouldn't be sitting here talking about it.
If we connect this to the bigger picture, no, we absolutely would not be here. The biosphere, every living thing on this planet survives because of the Earth's magnetic field.
It deflects the solar wind, right?
It does. It deflects the solar wind. It stops our atmosphere from being stripped away into space like what happened to Mars. And that magnetic shield is generated by the geodynamo.
Right, the geodynamo, which is essentially a massive churning ocean of liquid metal in the outer core, spiraling around and creating electrical currents.
Exactly. And those currents create the magnetic field. But for that liquid metal to churn, you need convection. You need a temperature difference.
Okay, like heat rising.
Yes. The inner core is solid and vastly hotter than the outer core. So heat is trying to escape from the center of the Earth out toward the mantle.
And that makes it boil.
That escaping heat is what causes the liquid metal to boil and churn, much like water rolling in a pot on a hot stove.
Okay, so where does the nickel come in?
Well, for a long time, geophysicists had a paradox on their hands. Pure iron has a very high thermal conductivity. It's incredibly efficient at passing heat along.
Okay, so it just lets the heat out.
Right. If the outer core were purely liquid iron, the heat from the inner core would just smoothly and quietly conduct outward through the metal. It would pass from atom to atom without the need for the liquid metal itself to physically move.
And if the liquid isn't physically moving, it's not churning, it's not convecting.
Exactly. If the heat just conducts away efficiently, the liquid stays relatively still. No convection means no geodynamo.
And no geodynamo means no magnetic field.
Which means a dead, irradiated planet.
Okay, wait. Let's unpack this. I think I see where this is going. So, is the nickel acting like a speed bump?
That is a brilliant way to conceptualize it.
So under the extreme crushing pressures of the Earth's core, which are, what, millions of times greater than at the surface?
Yes, immense pressure.
The atomic behavior of these metals changes, and the electrons in nickel scatter much more frequently than the electrons in iron.
That's right.
So the heat is trying to take the fast lane out of the core, hopping smoothly from iron atom to iron atom, but then it hits a nickel atom, and the electrons are just chaotic, scattering the energy. It's basically a microscopic traffic jam.
Yes. By acting as an atomic impurity, the nickel significantly lowers the thermal conductivity of the overall alloy. It chokes the ability of the iron to just quietly pass the heat along.
So it forces a physical reaction.
Exactly. Because the heat can't escape efficiently via conduction, the temperature differential builds up. The system becomes unstable.
It has to release the heat somehow.
The only way for the Earth to release that trapped, blistering heat is to force the molten metal itself to physically rise. It forces convection.
So that traffic jam spins up our magnetic dynamo.
That spiraling, turbulent traffic jam of molten iron and nickel is the magnetic heartbeat of our planet. It is known in geophysics as the nickel effect.
A slight difference in electron scattering at the center of the Earth is fundamentally why we have blue skies, liquid water, and breathable air.
It really is.
That is just, it's almost too vast to comprehend. A subatomic quirk of a single trace metal is keeping us all alive.
It's incredible.
But let's look at the flip side, because while it's safely trapped down in the core playing the hero, the tiny, tiny fraction of it that actually made it up into the Earth's crust, which is only about 80 parts per million, has a much more, well, devilish reputation historically.
It does. In fact, if you look at the etymology, its very name translates to the devil.
I love this story from the sources. So set the scene for us. We're in the 15th century, right?
Yes. In the Ore Mountains of Saxony, in modern-day Germany, miners are digging deep underground and they stumble across this rich, reddish-brown ore.
And they think it's copper.
To them, it looks exactly like copper ore. They think they've hit the jackpot, but when they haul it up and throw it into their smelting furnaces, it completely fails to yield a single drop of copper.
Nothing at all.
Not a drop. And the failure wasn't just economic, it was biological. The smelting process released these incredibly thick, toxic, garlic-scented fumes.
Garlic-scented, that sounds horrible.
It was. The miners who breathed it in became violently ill, suffering from severe respiratory issues and poisoning.
Imagine being a 15th century miner. I mean, your job is already a nightmare of darkness and danger. And suddenly this rock that looks like treasure is actively poisoning your friends and smells like demonic garlic.
They were deeply superstitious communities. So quite logically for the time, they blamed it on a mischievous mine spirit, a goblin or a devil figure they called Old Nick.
Oh.
They named the deceptive rock Kupfernickel, which roughly translates to Old Nick's copper or the devil's copper.
And what were they actually breathing in? What was making that garlic smell?
Arsenic.
Oh, wow, arsenic.
Yeah, the ore they had found wasn't copper at all. It was a mineral called nickeline, which is an alloy of nickel and arsenic.
Oh, so when they burned it...
When they heated it in the roasting furnaces, they were vaporizing the arsenic into a highly toxic gas.
That's terrifying.
It took hundreds of years to figure that out, too. It wasn't until 1751 that a Swedish chemist named Axel Fredrik Cronstedt finally managed to isolate the true metallic element from this cursed rock.
So he figured out what it really was.
He stripped away the arsenic, found this silvery white metal, and decided to just keep the folklore alive. He shortened the name to nickel.
So we have a metal on the periodic table named after a goblin. That is fantastic.
It's a great piece of history.
But if this stuff is so rare in the crust, like you said, 80 parts per million, how do we actually get our hands on enough of it to build modern civilization? How does the Earth concentrate it into deposits we can mine?
Geology essentially uses two primary methods to scrape together those trace amounts into massive, economically viable deposits.
Okay, what are they?
One happens deep underground in fiery magma chambers, and the other happens right on the surface in tropical rainforests. Let's start with the underground process, magmatic sulfides.
Like the deposits in Sudbury or Norilsk.
Exactly.
Walk me through how a magmatic sulfide deposit forms, because magma coming up from the mantle already has trace nickel in it, right?
It does. Mafic magma, which is hot, fluid, and rich in iron and magnesium, naturally contains trace amounts of nickel. But usually that magma is undersaturated in sulfur.
Meaning there's no sulfur in it yet.
Right. Because there's no sulfur around, the nickel ions just stay happily dissolved in the molten silicate rock, or they hide inside the crystal lattice of early forming minerals like olivine.
So it's just spread way too thin to ever be useful to us.
Exactly. To form an ore deposit, you need a chemical trigger. The magma has to encounter an external source of sulfur as it travels upward through the crust.
Like it has to hit a specific type of rock?
Yes. Often this happens when the searing hot magma violently intrudes into sulfur-rich sedimentary rocks, like ancient black shales or evaporites, and melts them.
Okay.
This triggers a sudden chemical crisis in the magma known as sulfur saturation.
And this creates a separation process, right? I've seen this compared to oil and water in the sources.
It's a very accurate comparison. Suddenly, an immiscible sulfide liquid forms within the silicate magma. They fundamentally cannot mix.
So they separate.
So you have a silicate melt, and scattered throughout are these tiny liquid droplets of pure sulfide. And here is the critical behavioral trait of nickel. It is highly chalcophile.
Chalcophile, what does that actually mean in this context?
It means it loves sulfur. If given the choice between staying in a silicate rock or bonding with sulfur, nickel will choose sulfur every single time.
Oh, I see.
So as these sulfide droplets form, the nickel completely abandons the surrounding silicate magma and jumps into the sulfide liquid. It's basically a chemical sponge soaking up all the trace metals.
Okay, but how does that give us a massive chunk of ore to mine? You still just have a bunch of microscopic droplets floating around in a volcano.
Gravity takes over.
Oh.
Because these sulfide droplets are incredibly dense, around 4.5 to 5 grams per cubic centimeter, compared to the surrounding magma, which is much lighter, maybe 2.7, they sink.
They just fall to the bottom.
They literally rain down through the liquid magma chamber. They pool at the bottom, or they get caught in physical choke points in the volcanic plumbing system, aggregating into massive, solid lenses of pure nickel-copper sulfide.
So it's basically a giant subterranean metal trap.
It really is.
And I know geologists look for something called the R factor when evaluating these.
Yes, the R factor is crucial. It stands for the ratio of silicate magma to sulfide melt.
Why does that matter?
If you have a high R factor, it means a very small amount of sulfide droplets has interacted with a massive roaring river of magma.
Oh, so they've had more magma to pull from.
Exactly. Those few droplets have had the chance to scavenge trace nickel from a vast volume of rock. The resulting sulfide pool will be what we call high tenor or incredibly rich, concentrated, and valuable.
Okay, so that's the magmatic process. Fire, molten rock, sulfur sponges, and gravity.
Right.
But the second way Earth concentrates nickel is the complete opposite. It's slow, wet, and happens entirely on the surface. Laterites.
Yes, laterite.
Talking about places like New Caledonia and Indonesia, which the sources describe as essentially the tropical nickel factories of the world.
Laterite deposits are monuments to the sheer power of time and water. They form through intense, relentless chemical weathering.
Just weathering.
We are talking about millions of years of heavy tropical rain beating down on exposed, ultramafic rocks that have been pushed up from the ocean floor.
Wait, you're telling me rain can turn a rock that is like a 0.18% trace rock into a 3% commercial ore just by washing away the other stuff?
Yeah.
Is it really that simple, or is there a catch?
It sounds absurd, I know, but yes, it is that simple. It's a process of secondary enrichment, and it creates a layered soil profile that can reach 50 meters deep.
50 meters of dirt.
Yeah, picture a single drop of slightly acidic rainwater hitting the surface. At the very top of the ground, you have the dirt crust, a hard baked iron cap. The water percolates through that and enters the limonite zone.
The limonite is that classic deeply red and yellow tropical dirt, right?
Exactly. In this upper zone, the environment is highly acidic and oxidizing. Over millions of years, the rain literally dissolves the primary minerals.
So it just melts the rock away.
It takes the silica and the magnesium that make up the bulk of the rock, breaks them down into a solution, and flushes them away into the groundwater system. They are gone.
Wow.
What gets left behind are the elements that refuse to dissolve easily, primarily iron and aluminum oxides.
So where is the nickel hiding in all this red dirt?
The nickel acts like a survivor. As the rock dissolves around it, it gets trapped or scavenged within the crystal lattice of those remaining iron oxides, specifically a mineral called goethite.
Oh, I see.
It's the last man standing concept. You've washed away 80% of the original rock's mass, so the nickel concentration naturally spikes simply because everything else left the party.
But that's just the top layer, right? The really valuable stuff is deeper down in the profile.
Yes. As that rainwater continues to percolate downward, carrying a tiny bit of dissolved nickel with it, it reaches the saprolite zone.
And what happens there?
Down here, closer to the unweathered bedrock, the chemistry changes. The pH rises. It becomes less acidic. The nickel that was leaching downward suddenly becomes insoluble again and precipitates out of the water.
So it's double dipping. It's getting the nickel left behind, plus the nickel washing down from above.
Precisely. It undergoes what we call absolute enrichment. The nickel actually substitutes for magnesium in newly forming clay minerals.
And that changes the color.
It creates incredibly vibrant, almost neon green hydrosilicates, commonly known as garnierite. If you see a rock with thick, bright green veins running through it, that's garnierite.
That sounds beautiful.
In the saprolite zone, those green veins can contain astonishing grades of 20 to 40% pure nickel.
But nature is a delicate balancer. I was reading that for a laterite deposit to actually form and survive, the tectonic plates have to be cooperating perfectly.
It is a razor-thin margin of error. These deposits form on land that is actively uplifting.
Like being pushed upward.
Right. If the tectonic uplift is too slow, the topography goes flat, the water stops draining, and the weathering stalls. Even worse, the rain just washes the entire deposit into the ocean.
Oh, so you lose it all.
Exactly. But if the uplift is too fast, mountains form, erosion speeds up, and the deep soil profile gets stripped away before it can ever mature.
So it has to be perfectly paced.
New Caledonia holds about 25% of the world's laterite resources, specifically because it has maintained that perfect, agonizingly slow balance of uplift and tropical weathering for tens of millions of years.
It's incredible how many things have to go right. So we have laterites forming slowly in the rain and magmatic sulfides forming violently underground.
Right.
But let's rewind the clock 252 million years, because the formation of one of those specific magmatic sulfide deposits, the massive Norilsk deposit in Siberia, didn't just create an ore body.
No, it did not.
The process of it forming almost ended the world.
The Permian-Triassic mass extinction, paleontologists often just call it the Great Dying.
The Great Dying, it sounds ominous.
It is the most catastrophic extinction event in the fossil record.
Okay.
90% of marine species and 70% of terrestrial vertebrate species just vanish.
90%. That's almost a total reset.
And for decades, the exact kill mechanism was a subject of fierce debate.
Right, because we knew the Siberian traps erupted. This was a large igneous province. We're talking about volcanoes pumping out 1.5 million square kilometers of lava.
A staggering amount of lava.
But Earth has had massive volcanic eruptions before. Why was this specific one so universally apocalyptically lethal?
Well, the answer wasn't just geological. It was biological.
How so?
It came down to a specific strain of marine archaea, a single-celled organism called Methanosarcina. Around this exact time in Earth's history, through a process called horizontal gene transfer, Methanosarcina stole a gene from a bacterium.
Like it just absorbed it.
Yes, and this new gene gave it a devastating new metabolic superpower. It acquired the ability to convert acetate directly into methane.
Methane, which is a tremendously potent greenhouse gas.
Yes, and the Permian oceans were stagnant and loaded with massive untapped reservoirs of organic carbon just sitting on the seafloor.
So it was like a giant buffet.
This archaea suddenly had the genetic code to eat all of it and turn it into a climate-destroying gas. But there's a bottleneck.
What stopped it?
To perform this conversion on a planetary scale, Methanosarcina needed massive amounts of a specific supernutrient to build the required enzymes.
Let me guess. It needed nickel.
It needed nickel.
But wait, this is where I get confused. We just established that nickel is a heavy, dense metal. It's non-volatile. During a volcanic eruption, its whole identity is to sink to the bottom of the magma chamber in those heavy sulfide droplets.
Exactly. It wants to sink.
So how on earth did millions of tons of heavy metal get out from miles underground up into the atmosphere and disperse globally across the oceans to feed a microbe?
That was the defining geological mystery. How do you make a heavy metal fly?
Right.
The answer was discovered frozen in place, locked inside the deep unmined rocks of the Norilsk ore body itself. Geologists were looking at these deep cumulate rocks under microscopes, and they found a very peculiar microscopic texture.
What do they call them?
They termed them capped globules.
Paint a picture for me. What does a capped globule look like under a microscope?
Imagine a tiny spherical void space in the rock. Sitting at the very bottom of this void is a heavy, frozen droplet of sulfide. That's the dense, nickel-rich ore.
Okay, the heavy part.
But sitting right on top of it, completely filling the rest of the void space, is a cap of late crystallizing silicate minerals. We're talking highly differentiated stuff like clinopyroxene and apatite that is rich in chlorine.
Okay, so it's a two-part package, a heavy sulfide base and a lighter silica hat. How does that prove the nickel went airborne?
Because it captures a dynamic mechanism called gas filter pressing frozen in time.
Gas filter pressing.
As the magma in these massive underground sills slowly cooled and crystallized, the volatile gases dissolved in the rock began to fall. They formed bubbles.
Like carbonation in a soda.
Exactly like that. And because of the complex surface tension dynamics between the silicate melt, the liquid sulfide, and the expanding gas, these vapor bubbles physically attach themselves to the heavy sulfide droplets.
Ah, I see. So is it kind of catching a ride? Like a hot air balloon, where the expanding gas bubble is the balloon and the heavy sulfide droplet is the basket hanging underneath.
Mechanically, that is a fantastic analogy. The vapor bubbles provided the necessary buoyancy to offset the density of the metal.
So it actually lifted it up.
They literally floated the heavy nickel sulfides up through the magma column toward the erupting vents. But it wasn't just physical transport. A violent chemical reaction was happening inside those bubbles as they rose.
Right, because the magma had melted the surrounding crust to get its sulfur, like we talked about earlier.
Exactly. And in Siberia, the specific crust that the magma melted through contained massive, ancient salt beds evapotite rocks.
Salt beds. So lots of chlorine.
This made the Siberian Traps magma incredibly saturated with chlorine. Under the extreme heat and dropping pressure of the ascent, the chlorine gas inside the bubble reacted chemically with the attached nickel sulfide basket.
Oh, wow. What did it do?
The chlorine literally stripped the nickel atoms out of the sulfide melt and formed a new gaseous compound, nickel chloride.
So the heavy metal didn't just float, it chemically transformed into a gas.
It did. When those highly pressurized, volatile-rich lavas finally breached the surface and erupted, they violently exhaled vast quantities of gaseous nickel chloride into the atmosphere.
And then what happens to the gas?
Once it hit the cooler air, it rapidly condensed into solid, microscopic aerosol particles. These particles fell perfectly into what atmospheric scientists call the accumulation mode, about 0.1 to 1 micrometers in diameter.
Which is the exact sweet spot for staying airborne, isn't it? Too small to fall out quickly, too big to be easily scrubbed out by rain, small enough to float on the wind for thousands of miles.
Precisely. They rode the stratospheric winds across the entire globe. And the reason we know this isn't just a hypothesis is because we have an isotopic smoking gun.
Ooh, a smoking gun. What is it?
What's fascinating here is that geologists analyzed ancient sedimentary black shales from the Sverdrup Basin in the Canadian Arctic. Back in the Permian, this basin was an ocean directly downwind of the Siberian Traps. When they tested those rocks, they found an isotopic signature of nickel that is described as exceptionally light.
Light isotopes like
Yeah.
nickel-60.
Yes. They found negative values going all the way down to minus 1.1 per mil. In geology, almost all normal sedimentary rocks on Earth have heavy nickel isotope signatures.
So where does the light signature come from?
The only known geological process capable of producing a signature that light is the high-temperature fractionation that happens during the formation of magmatic sulfides.
Wow.
Finding that exact extreme signature buried in Arctic Ocean sediments proves beyond a shadow of a doubt that the nickel from the deep underground Norilsk magma chambers was physically transported through the atmosphere and rained down across the planet.
That is just terrifyingly elegant. So let's put the whole apocalyptic sequence together from the sources.
Go for it.
The Norilsk volcanoes erupt. The chlorine gas acts like a hot air balloon, strips the nickel, floats it to the surface, and aerosols it across the stratosphere.
Right.
It rains down globally into the oceans. The Methanosarcina archaea suddenly wake up to find an unlimited global buffet of the exact microscopic nutrient they need to build their enzyme.
Missing puzzle piece.
They bloom on a scale we can't even fathom. They pump out unthinkable amounts of methane. The global climate drastically warms. The oceans acidify. The water loses its oxygen. And 90% of all life on Earth suffocates and dies.
Exactly.
All because of a chemical reaction in a microscopic gas bubble.
It is the ultimate butterfly effect.
Yeah.
It is a profound, almost sobering demonstration of how deeply chemically interconnected the solid inorganic Earth is with the fragile biosphere.
Which naturally leads to the next massive question. Why did that specific microbe need nickel so badly?
That's a great question.
Like, if that microbe used nickel as a metabolic supercharger to destroy the world, is nickel doing that to living things right now? What is it about this specific metal that makes it the biological key to life?
It absolutely is doing it right now. In fact, nickel is officially classified as a fundamental, essential micronutrient for all plant life.
All plants?
Yes, all plants. It was only officially recognized as such recently, in 2004, because the amounts required are so vanishingly small that it took decades of precise hydroponic testing to prove it.
How small are we talking?
Plants require less than 0.001 milligrams of nickel per kilogram of dry weight. But if you remove that microscopic trace, critical biochemical pathways completely shut down.
And it all centers around one specific enzyme, right? Urease, which, fun fact I learned from the material, was actually the very first enzyme ever crystallized in human history. A scientist named James Sumner did it back in 1926.
That's a great piece of trivia. And yes, it centers around urease. Urease is a massive complex protein. But here's the catch.
Yeah.
By itself, the urease protein is essentially a useless, inert lump.
It doesn't do anything.
Nothing. It requires a spark. It requires activation. Inside plant cells, there are highly specialized accessory proteins specifically named ured, uref, and ure.
Okay, accessory proteins, what do they do?
You can think of them as a microscopic molecular construction crew. Their entire evolutionary purpose is to hunt down exactly 2 nickel atoms and meticulously install them at the active site of the urease protein.
Wait, just 2 atoms?
Just 2 atoms. They are installed separated by a microscopic gap of just 3.5 angstroms, and they are held perfectly in place by a modified amino acid called a carbamylated lysine residue.
That sounds incredibly precise.
The precision is staggering. But once those 2 nickel atoms are locked into the active site, the urease enzyme wakes up, it changes conformation and becomes highly reactive.
And what's its job once it's awake?
Its singular job is to find urea, which is a nitrogen-rich compound that plants use to safely transport nutrients from their roots to their leaves, and hydrolyze it.
So it breaks it down.
It breaks the urea molecule apart, releasing usable ammonia for the plant to build proteins and carbon dioxide.
Okay, so what happens if a plant is growing in a soil that is completely devoid of nickel? What happens if the construction crew can't find those two atoms?
If there's no nickel, the urease stays permanently inactive.
Oh.
The plant continues to absorb nitrogen from the soil and pack it into urea to move it around. But when that urea reaches the end of the line, usually at the very tips of the expanding leaves, the plant has no way to break it down.
So it just piles up.
The urea just builds up and builds up until it reaches toxic concentrations, physically poisoning and killing the plant's own cells.
And there's a very specific visual manifestation of this in agriculture, isn't there? The mouse ear deformity in pecan trees.
Yes, the mouse ear deformity. Pecan trees transport a massive amount of their nitrogen as ooids during the spring flush of growth.
Okay.
If an orchard is nickel deficient, the toxic urea buildup at the leaf tips causes the new leaflets to become stunted. The tips die off, leaving a rounded, wrinkled, necrotic leaf that literally looks like the rounded ears of a mouse.
Oh, wow. I can picture that.
For decades, farmers were baffled. They sprayed fungicides, they thought it was a new virus or late frost damage.
But it was just missing nickel.
It was entirely physiological.
Yeah.
It was simply the catastrophic failure of a single enzyme because it was missing two atoms of a heavy metal.
So on one hand, if a plant is missing a trace amount, it poisons itself with urea. But on the other hand, if a plant gets too much nickel, it acts like a toxic heavy metal poison.
Exactly. It's highly toxic in large doses.
Which is why those Saxony miners got sick and why industrial nickel runoff is an environmental disaster. So how do we explain hyperaccumulators?
Oh, these are fascinating.
Right, because the material highlights these mutant plants that seem to actively defy everything we know about toxicity. They suck up massive, lethal amounts of nickel deliberately.
Ah, the hyperaccumulators. They are botanical marvels. They turn the entire concept of toxicity on its head.
Give me an example.
You have plants like Alyssum berkeloni in the Mediterranean, or an astonishing tree called Phyllanthus belgui found in Southeast Asia. These plants have evolved to thrive on serpentine soils weathered from ultramafic rocks that are naturally laced with lethal levels of heavy metals.
So they just live in toxic dirt.
But instead of just tolerating the hostile soil or trying to block the nickel from entering their roots, they actively pump it up into their tissues.
Why would they do that?
Phyllanthus belgui is so extreme in this behavior that if you cut its bark, it bleeds literal bright green phloem sap. And that sap contains up to 16% pure nickel by weight.
16%? That's not sap, that's practically liquid ore. How do they not instantly kill themselves? If two atoms wake up an enzyme, what does billions of atoms do? What is the evolutionary trick to surviving that?
The trick is a masterpiece of biochemical compartmentalization. The plants know the nickel is highly reactive and dangerous.
Right.
So as soon as the nickel ions enter the roots, the plant synthesizes specific organic acids like citric acid or malate. These acids act as chemical chelators.
Chelators, what's that?
They bind to the nickel ion, essentially wrapping the toxic metal in a safe organic chemical cage. Once caged, the plant's transport proteins pump these chelated nickel molecules directly into the vacuole.
The vacuoles being the sort of storage closets of the plant cell.
Exactly. They lock the caged nickel away in the storage closet, completely isolating it from the delicate metabolic machinery floating around in the rest of the cell.
Ah, so it can't do any damage.
Right. The nickel can't interact with any enzyme, so it can't cause oxidative stress or toxicity.
But why expend all that biological energy to do this? Why bother pumping toxic metal into your storage closets in the first place?
It is the ultimate defense mechanism. The world is full of herbivores, caterpillars, and pathogenic fungi that want to eat those leaves.
Oh, I see where this is going.
If you are a caterpillar and you take a bite out of a leaf that is pumped full of 16% chelated heavy metal, you are going to experience acute heavy metal toxicity. You will die.
Wow.
By hyperaccumulating nickel, these plants are building a systemic, highly effective suit of toxic armor against the rest of the food chain.
And humans, being the opportunistic creatures we are, have figured out a way to exploit this mutant superpower, haven't we? Agromining.
Or phytomining, yes. It's a brilliant synergy of biology and metallurgy. We can deliberately plant these hyperaccumulator species on industrially contaminated soil or over low-grade laterite deposits that aren't economical to dig up with excavators.
So the plants do the mining for us.
The plants act as solar-powered biological miners, using their roots to meticulously pull the nickel out of the dirt. We then harvest the mature plants, dry them, and carefully incinerate them.
And burn them.
Yes. The resulting ash, which we call bio-ore, can contain anywhere from 10 to 20% pure nickel.
Which is a vastly higher grade than almost any natural rock ore you pull out of a traditional mine.
Easily. It is a completely renewable, environmentally regenerative method of extraction.
I love that. Plants harnessing the extreme, dangerous properties of this metal just to survive, which is, frankly, exactly what human beings do, just in a much louder, much more explosive way.
That's a good point.
We use the extreme properties of nickel to push the absolute physical limits of engineering, which takes us out of the soil and up into the sky. Let's talk about aerospace and the engines that allow commercial air travel to exist.
If you want to talk about hostile environments, the inside of a modern jet engine might be the most extreme, sustained engineering environment humanity has ever created.
How hot does it actually get?
Well, the high-pressure turbine blades inside those engines are spinning at thousands of revolutions per minute, subjecting the metal to immense centrifugal forces. And they're doing this while bathed in combustion gases that are literally white hot.
Jeez.
The operating temperatures inside these engines routinely reach 0.85 of the melting point of the metal itself.
Wait, let me stop you there. Because if you take a piece of metal, heat it up until it is at 85% of the temperature required to turn it into liquid magma, and then you pull on it with the force of a spinning turbine.
It should fail.
It shouldn't hold its shape, it should just stretch out and deform like warm taffy.
It absolutely should. In metallurgy, that physical deformation under heat and stress is called creep. It is the enemy of structural integrity.
So how do they stop it?
The turbine blades don't stretch because they aren't made of ordinary steel or titanium. They are made of nickel-based superalloys.
The superalloys.
And these superalloys resist, creak through an incredibly elegant, almost paradoxical crystallographic trick. Inside the primary matrix of the metal, metallurgists induce the precipitation of a secondary microscopic structure called the gamma prime phase.
The gamma prime phase. What does that actually look like inside the metal?
They are microscopic, highly ordered, perfectly cubic crystals composed of nickel tightly bonded with elements like aluminum and titanium.
Okay, little cubes.
They precipitate out and sit embedded within the softer primary nickel matrix, almost like microscopic bricks in a wall of mortar.
Okay, so you have hard, ordered cubes mixed into the metal. How does a cube stop the blade from stretching like taffy?
To understand that, you have to understand how metal deforms at the atomic level. When metal stretches, it doesn't just pull apart cleanly.
How does it stretch then?
It deforms through the movement of dislocations, which are essentially tiny imperfections or misalignments in the atomic lattice that slide past each other, like a wrinkle moving across a rug.
Oh, I like that analogy. A wrinkle in a rug.
When one of these gliding dislocations hits one of these highly ordered gamma prime cubes, it hits a wall. It can't just slide through because the atomic arrangement in the cube is too strict.
So it gets stuck.
To pass through, the dislocation is forced to pair up with a second dislocation, forming a massive, bulky complex called a superdislocation.
A superdislocation? That sounds like it requires a massive amount of force to move.
It does. It requires a tremendous amount of thermal and mechanical energy to shove a superdislocation through that ordered cube. And here is where the physics of nickel superalloys gets truly bizarre.
How bizarre.
These alloys exhibit a property known as inverse temperature dependence.
Inverse temperature dependence, meaning it acts backwards to heat.
Exactly. Normally, as any material gets hotter, the atoms vibrate more, the bonds loosen, and it gets softer and weaker.
Right, like ice melting into water.
But in a nickel superalloy, as the temperature climbs to extreme searing levels, the physical energy required to move that superdislocation through the gamma prime lattice actually increases.
Wait, really?
Up to a certain critical threshold, the metal effectively gets stronger and more resistant to deformation the hotter it gets.
That defies all common sense. It gets stronger as it gets hotter.
It is a quantum mechanical quirk of the lattice structure. And that specific bizarre resistance is the only reason the turbine blade doesn't rip itself apart at 30,000 feet.
That is just, wow.
But metallurgists have to be incredibly careful. It is a precarious balance. Because at those extreme temperatures, if the alloy chemistry is even slightly off, the metal can sometimes form what are called TCP phases. Topologically close-packed phases.
What are TCP phases?
They are the enemy within. TCP phases are highly brittle, plate-like structures that can precipitate out of the alloy during operation.
Oh, that doesn't sound good.
If a TCP phase forms, it acts like a microscopic knife inside the metal. It robs the surrounding alloy of its strengthening elements and creates a fast track for cracks to propagate. It turns a blade that can withstand immense stress into a blade that shatters.
Wow, so the mastery of nickel literally lets us defy gravity and fly. But as impressive as aerospace is, nickel's most critical modern role, the reason it is dominating headlines right now, is on the ground.
Yes, on the ground.
We have to talk about the green energy transition. Nickel is the absolute heart of the lithium-ion batteries that are powering the electric vehicle revolution.
Yes. Specifically, it's the primary component of the battery cathodes. If you look at the most advanced high-performance EV batteries on the market today, like the NMC 811 chemistry,
What does NMC stand for?
it stands for nickel, manganese, and cobalt in a ratio of 8 to 1 to 1, and they rely overwhelmingly on nickel. Nickel is the element that provides the high energy density.
The driving range, basically.
It's the reason an electric car can hold enough charge to drive 300 or 400 miles before needing to plug in.
And the battery industry is actively trying to stuff even more nickel into these cathodes, right? To phase out the cobalt.
Exactly. Cobalt is expensive, and its supply chain is fraught with severe ethical and human rights issues, particularly concerning mining practices in the Democratic Republic of Congo.
So they want to use more nickel instead.
So the goal is to maximize the nickel. But this insatiable, exponential demand for battery-grade nickel has triggered a frantic global scramble. And it's aggressively reshaping global geopolitics, with the absolute epicenter being Indonesia.
Right, because as we discussed earlier, Indonesia holds massive, sprawling reserves of those tropical laterite deposits, the red dirt and the green garnierite.
Yes.
Historically, what was their role in the market? They just dug up the dirt and put it on ships.
Historically, they were a raw material exporter. They mined the laterite ore and exported the raw, unprocessed dirt, mostly to China, where it was smelted down to make stainless steel.
Okay, that makes sense.
But in 2020, the Indonesian government made a radical, highly aggressive economic move. They instituted a strict, total ban on the export of raw nickel ore.
They just shut off the tap to the rest of the world.
Overnight, the message was clear. If the world wants our nickel to build their clean energy future, they can't just take our dirt.
They have to process it there.
They have to come here, bring their capital, and build the multi-billion-dollar processing refineries on Indonesian soil. They forced the supply chain to domesticate.
And it worked, didn't it?
From an economic standpoint, it's a masterstroke. Foreign investment flooded in. They successfully cornered the global supply growth. But here is the massive looming problem.
What's the catch?
Processing that wet, low-grade laterite ore into the high-purity battery-grade chemical nickel needed for EVs is not like smelting sulfides. You can't just melt it.
Why not?
It requires a brutally intense chemical process called HPAL, high-pressure acid leaching.
Break down HPAL for me. How does it work?
You take that limonite dirt, you grind it into a slurry, and you pump it into an immense titanium-lined pressure cooker called an autoclave.
An autoclave. Got it.
You inject massive volumes of highly concentrated sulfuric acid, and you heat the entire highly corrosive mixture to over 250 degrees Celsius at extreme atmospheric pressure. It cooks the rock, dissolving the nickel out of the iron oxides.
That sounds like it requires a staggering amount of power to run.
It does. It is incredibly energy intensive. And in Indonesia, the electricity grid powering these massive HPL facilities is largely fueled by burning captive coal.
Burning coal.
So you are burning coal to get the metal for clean cars. But it gets worse.
Oh, no.
When the HPL process is finished and you have successfully extracted the 1% of nickel, you are left with 99% of the rock as a highly acidic, toxic waste slurry loaded with heavy metals.
The tailings.
These are the tailings. Managing millions of tons of wet, toxic tailings in a tropical rainforest that experiences frequent earthquakes and torrential monsoons is an environmental nightmare.
So let me get this straight. We are essentially clear-cutting tropical rainforests, strip mining the soil, burning massive amounts of coal to heat gigantic titanium vats of boiling sulfuric acid, and generating literal lakes of toxic waste.
That's the reality.
All to get the metal we absolutely require to save the environment with zero-emission electric vehicles. That is a terrifying, hypocritical trade-off.
It is widely referred to in the industry as the green dilemma. The EV revolution urgently requires clean batteries. But right now, the supply chain is being flooded with dirty nickel.
So it's counterproductive.
The carbon footprint of extracting it almost negates the environmental benefit of the electric car it goes into. This profound contradiction is causing extreme volatility and anxiety in the global market.
Automakers must be freaking out.
Automakers are desperate. They're scouring the globe trying to find sources of green nickel mined with a low carbon footprint and low environmental impact to satisfy tightening environmental regulations and consumer demands.
Well, the good news is we aren't going to end this deep dive on a note of doom because our final set of research points to a completely different, almost miraculous type of geology that might actually solve this exact dilemma.
It's a really exciting development.
We're talking about a unique mineral called Awaruite.
Awaruite is a fascinating geological outlier. Its chemical formula is Ni3Fa, meaning it is composed of 3 parts nickel to 1 part iron.
Okay.
Crucially, it is a naturally occurring pure metallic alloy.
Which means it lacks the bad stuff, like the stuff that makes processing it toxic.
Exactly. It is not a magmatic sulfide, which means there is no sulfur to release acid rain or toxic sulfur dioxide gas when you process it.
Right.
And it's not a laterite soil, which means you don't need to cook it in boiling vats of sulfuric acid in a coal-powered HPAL plant.
But where does a pure metal alloy just naturally form in the ground? That seems unusual.
It is found exclusively in serpentinized rocks. Serpentinization is a fascinating low-temperature metamorphic process.
How does it work?
Imagine deep mantle rocks, rich in the mineral olivine, being pushed up by tectonic forces and interacting with groundwater. The water reacts with the olivine.
So it's a water rock reaction.
The reaction heavily alters the rock into a softer green mineral called serpentine. But more importantly, the chemical reaction releases free hydrogen gas.
Okay, hydrogen gas.
This hydrogen creates a highly reducing environment, an environment starved of oxygen. Under those specific conditions, the trace nickel is stripped out of the silicate minerals and aggregates into these tiny, incredibly dense, highly magnetic flecks of pure awaruite metal embedded in the rock.
That's amazing.
There is a massive deposit of this currently being developed in British Columbia, Canada, known as the Baptiste deposit.
Okay, so if it's highly dense and highly magnetic, processing it should be easy, right? You just crush the rock up, run it down a chute, and pull the awaruite out with giant magnets and gravity.
You can certainly do a rough initial sort that way. But to get a true high-grade commercial concentrate suitable for the demanding battery chemical market, magnets aren't enough.
What do you need then?
You need to use a widespread metallurgical process called flotation. And this is where a major game-changing breakthrough detailed in our research occurred.
Let's get into the weeds on this. How does standard flotation work?
Normally, in froth flotation, you grind the ore up into a fine mud or slurry and put it in a massive tank of water. You add a specific chemical called a collector.
What does the collector do?
The collector's job is to selectively seek out and chemically stick only to the valuable metal particles, ignoring the waste rock. Once the collector binds to the metal, it makes the surface of the metal hydrophobic water repellent.
Okay, so it hates water now.
Then you bubble air up through the bottom of the tank.
And because the metal now hates water, it clings to the air bubbles.
Precisely. The valuable metal hitches a ride on the rising air bubbles, floats to the surface, and forms a thick metallic froth that you simply skim off the top. The waste rock stays at the bottom. It's a highly effective standard industry practice.
But when they tried to float the awaruite from the Baptiste deposit, it failed, right? It wouldn't float. Why?
It was a problem of pH. The natural pH of this crushed, serpentinized rock slurry was highly alkaline, sitting naturally at a pH of 9.8.
Why so high?
This is because the host rock contained a lot of a mineral called brucite, which is a magnesium hydroxide that naturally raises the alkalinity of water.
Okay.
At that specific high pH of 9.8, the surface of the awaruite metal particles naturally reacts with the water to form a microscopic protective passivation layer of nickel oxide.
Like a microscopic layer of rust shielding the metal.
Exactly. And the standard chemical collector they were using, an industry standard chemical called xanthatate, fundamentally cannot bind to nickel oxide. It needs bare metal.
So it just slides off?
The xanthate just bumped into the oxide shell and slipped right off. The awaruite stayed hydrophilic, ignored the bubbles, and sank to the bottom with the waste.
Well, that's a huge problem.
The breakthrough they discovered was remarkably elegant in its simplicity. They just dropped the pH. They added acid to the slurry to lower the pH down to 4.5, making it weakly acidic.
Wait, so is the acid basically acting like a chemical exfoliant? Like when you wash your face with a salicylic acid to scrub off the dead skin cells, it just dissolves that dead oxide rust off the awaruite particle so the chemical collector can finally touch the healthy bare metal underneath?
That is the perfect way to visualize it. The weak acid environment chemically dissolves the passivation layer.
That's awesome.
Once that oxide dead skin is stripped away, the raw metallic Awaruite is exposed. The Xanthac collector instantly chemisorbs onto the blood surface, oxidizes into a compound called dexanthogen, and induces strong hydrophobicity.
And then it floats?
The Awaruite particles latch onto the bubbles and float beautifully to the surface.
That's brilliant, but I see an economic flaw here. Dropping the pH of millions of tons of rock slurry requires millions of gallons of acid, and acid costs a lot of money.
It does. If they just dumped acid into the raw slurry, the project would be bankrupt. Which leads to the second, crucial innovative step in the breakthrough process, desliming.
Desliming, like removing slime.
Yes. When you mechanically grind up serpentinized rock, it doesn't just break into neat little sand grains. It produces a massive volume of ultrafine, microscopic, powdery mud called slimes.
Okay, slimes.
These slimes have a massive surface area and are incredibly reactive. If you add acid, the slimes will instantly soak it all up like a sponge before the acid ever gets a chance to clean the Awaruite.
So you have to get rid of the slimes first. How do you even do that?
Before they add a single drop of acid, they pump the raw slurry through a device called a hydrocyclone. It's essentially an industrial centrifuge.
Oh, so it spins it.
It uses centrifugal force to separate the heavier, coarser particles, where the heavy Awaruite is, from the ultralight, powdery slimes. The hydrocyclone spins the slimes out and completely removes them from the flotation circuit.
So you're only acid washing the good stuff. How much acid does that actually save?
The numbers are staggering. Without desliming, they were consuming about 32 kilograms of sulfuric acid per ton of rock just to drop the pH.
Wow, that's a lot.
By mechanically removing the slimes first, they dropped the acid consumption down to just 12.8 kilograms per ton. It cuts the chemical cost by more than half, which completely changes the economic viability of the entire massive mine.
And when you combine the exfoliation and the desliming, what is the final result? What does this process actually yield at the end of the pipe?
It produces a stunningly high-grade concentrate of 40 to 45% pure nickel.
Wait, really? Is that high?
For context, a normal, highly successful magmatic sulfide mine considers a 5 to 15% concentrate to be a massive victory. A 45% concentrate is almost unheard of.
That's incredible.
Furthermore, this Awaruite concentrate is remarkably clean and have basically zero penalty elements. There's no toxic arsenic, no lead, no complex heavy metal contaminants that smelters usually penalize miners for.
But here's the absolute kicker, the thing that makes Awaruite the absolute holy grail of the green energy transition. It's not just about the metal, it's about the waste rock.
Yes, the tailings. The gangue material, the 99% of the rock left over after you extract the Awaruite, is predominantly made of serpentine and brucite.
Right.
These specific magnesium-rich minerals have an incredible innate natural capacity to undergo spontaneous mineral carbonation.
Meaning they react with carbon.
When they are crushed up and exposed to the air, they act like a chemical sponge for greenhouse gases. They absorb carbon dioxide directly in from the atmosphere and chemically lock it away, turning the invisible gas into stable, solid carbonate rock forever.
So if you run the numbers on that, a large-scale Awaruite mine could theoretically be entirely carbon neutral, or, if engineered correctly, potentially even carbon negative.
Exactly.
It would literally pull more CO2 out of the atmosphere to solidify its tailings than the diesel trucks and mills produce to mine it.
It represents a profound paradigm-shifting change in how we approach the metallurgy of the future. It skips the sulfur emissions of the sulfides, it completely bypasses the boiling toxic acid lakes and coal power of the HPA laterites, and it actively eats its own carbon footprint.
It's the ultimate clean metal.
It is the definition of green nickel.
It really seems like the perfect solution. And it brings us full circle. We have covered an unbelievable amount of ground today on this deep dive.
We really have.
We started by watching the thermal collapse of dying stars forging radioactive nickel in the deep cosmos. We dove down into the absolute molten center of the Earth to see how a microscopic electron scattering effect creates the magnetic traffic jam that keeps our atmosphere anchored to the planet.
It's quite a journey.
We learned how gas bubbles floated heavy metal out of Siberian volcanoes to trigger the Great Dying Mass Extinction. We looked at how 2 single atoms of nickel wake up the enzymes in pecan leaves, how hyperaccumulating plants use it as toxic armor, and how it stops jet turbine blades from tearing apart in midair.
And we didn't even get to everything.
And finally, we looked at how this one metal is currently sitting at the absolute center of a geopolitical tug-of-war for the future of clean energy, pushing us to find revolutionary carbon-absorbing rocks in British Columbia. Element 28 is doing a massive amount of heavy lifting for one tiny square on the periodic table.
I think if we step back and connect all of this to the bigger picture, it highlights a fundamental truth. Geology isn't just a static study of dead rocks sitting in the ground.
No, definitely not.
The Earth is an active, deeply interconnected, dynamic chemical system. The behavior of a single element dictates the evolution of biology, the stability of the climate, and the absolute outer limits of human technological progress.
It is deeply humbling. Now, before we wrap up, I know you always like to leave us with something to chew on. A final thought or a thread from the research that we didn't fully get to unpack. What do you have for us today?
We spent a lot of time today talking about the terrestrial frontiers of mining. The magmatic sulfides deep underground in Canada and Russia, the tropical laterites baking in Indonesia, and the promising serpentinites like the Awaruite in British Columbia.
Right.
But there's a fourth frontier of nickel mining that is dominating scientific debate right now, and we barely touched upon it.
Deep-sea polymetallic nodules.
The nodules at the bottom of the ocean.
Yes. Sitting quietly in the pitch-black abyss, scattered across the abyssal plains of the world's oceans, are estimated to be over 4.5 billion tons of ultra-high-grade nickel, copper, and cobalt.
4.5 billion tons?
They're just sitting right there on the sediment, waiting to be vacuumed up. Mining companies are currently designing massive robotic submersibles to go down and harvest them.
Wow, that would solve the battery shortage instantly.
Yeah.
But knowing what we've discussed today, I assume there's a catch.
There is a profoundly existential catch. Earlier, we noted that the serpentinization process, that exact low-temperature reaction where mantle rock meets water, releasing hydrogen and creating minerals like Awaruite.
That process doesn't just happen under mountains in Canada. It happens abundantly at the bottom of the ocean, at deep-sea hydrothermal vent systems.
Okay.
And right now, astrobiologists and geochemists consider those exact serpentinizing hydrothermal vents to be one of the absolute leading scientific candidates for the environment where life on Earth first originated billions of years ago.
Oh, wow.
It is the environment that likely provided the chemical energy, the hydrogen, and the elemental catalysts like nickel to spark the very first metabolic reactions.
That's huge.
So I leave you with this to consider. As humanity frantically rushes to dredge and mine the deep ocean floor to build the batteries for our clean, high-tech tomorrow, are we blindly risking the physical destruction of the exact type of ancient, delicate hydrothermal environments that birthed life on this planet in the first place?
Oh, man.
In our desperate attempt to save our future, are we destroying the cradle of our own genesis? It is the ultimate green dilemma, something to deeply think about.
A planetary savior and a planetary executioner to the very end. Thank you so much for joining us in this incredible deep dive into the source material. We'll catch you on the next one.